it's a velocity versus time graph. This is going to be the time here on the base, okay? And we start off knowing that. Nope, doesn't look like it. But the thing that we do know that's going to show up on here is this 20 meters. That's going to show up right there, okay? And I don't know the velocity yet, but that would go over here, okay? So I don't know the time. I don't know the velocity, but I do know the 20 meters. That just needs to be like a knee-jerk thing, and it's not yet for some of you, and that makes me sad in my heart. So you've got the change in position. That's the area in the velocity versus time graph, area between the graph and the axis, okay? And then you've got your free body diagrams and your force addition diagrams that kind of go along with that. This is all stuff we talked about on Thursday, but it's a 10 kilogram block. So this is 100 newtons, okay, of gravitational force. It's on a flat surface. There's no indication that there are forces at angles, so it's a pretty good guess that we've got a smoosh poosh of 100 newtons. And then this person's pushing with a 10 Newton horizontal force. And the force is frictionless, so there's no friction going the other way. So that's my FBD. And then when I go to draw my force addition diagram, I'm going to have 100 newtons up. I'm going to have 10 newtons to the right, as it were, and 100 newtons down. And so I'm going to end up with a 10 Newton FU. When you're drawing that FU, make it kind of a little bit thicker. And again, look at the direction of this thing. It's not following the directions that the other arrows use, okay? The FU begins at the beginning and it ends at the end. It's pointing the same direction as this arrow because that's how unbalanced the forces are. There's nothing to oppose that 10 newtons. So we're unbalanced by 10 newtons to the right. I can get the slope of this graph, the acceleration, from this equation. Acceleration equals FU over mass. So I'm going to have a 10 Newton FU divided by a 10 kilogram mass. That's going to give me an acceleration of 1 meter per second squared. So that's the slope on this graph. And then since I know that slope is going to be equal to the change in the vertical divided by the change in the horizontal, okay? I can kind of relate these things together. What if this is 1, to have a slope of 1 means that these two things are identical. So if this goes over 2, it must go up 2. If this goes over 3, it must go up 3, okay? If this goes over t, it's got to go up t because the slope is 1. So I can write this however I want. I can call this, oh gosh, what's a random letter? Let's call this Q, and this is Q. So this would be Q over Q, which is 1, okay? And then when I want to find the whole area of the triangle thing, 1/2 base times height, okay? The area is going to have to be 20 meters. The base of this thing is Q. The height of this thing is Q. 20 meters equals 1/2 Q squared. That means 40 equals Q squared. So Q is the square root of 40. Okay. We slap that in a calculator. And I get 6.32. And so that means that the base of this triangle must be 6.32 seconds. And the height of this triangle, because, I could go through and look at this in terms of units in the equation, or just look at this graph. It's a velocity graph. It's 6.32 meters per second. Okay. So those are like the examples of the hidden information I can find on these graphs. Okay. That's stuff we didn't know initially that we can figure out. But again, a lot of it comes from that velocity versus time graph. So while, this question is kind of like open-ended in terms of what it's asking you to draw, and you could draw an acceleration graph and you could draw a position versus time graph, all the things that we need are going to relate to that velocity versus time graph. Okay? now if we move on to part 2, so the person is going to once again apply a 10 Newton horizontal force to this 10 kilogram block. So it's the same problem, but now we're going to introduce a little bit of friction. So you've got a 10 Newton horizontal force, you've got a 10 kilogram block, but now you've got friction in the amount of 3 newtons between the block and the floor, okay? The person's going to, again, push it 20 meters. So follow the same process that we did the first time around. The difference is now you're going to need to add in 3 newtons friction, okay? So go ahead and have that on your whiteboard. So you don't need to erase your solution to problem 1, just modify it, maybe in a different color. What's going to change now that there's 3 newtons of friction? Pretty much always it starts from left. Now, if you saw it, it's going to slow down. So you're intending force that you're pushing, you're going to have to bring friction both ways. Yeah. Typically, temperature turns out from the push.
I respect that too.
No, that would be.
Well, we have to keep this in the shape. Because exactly just keep it. You don't have to. Oh wait, you want me to change this to 3? Oh, we just switched the
Just at least
Yeah, she does. Suck it away.
You should have been nice. So no one was like, oh, right? For this layup.
Yeah, I was at the game winner in your thing.
He's like,
I was at the game
yeah.
Sorry, Chase we got Nicky B. Nicky B comes for me. Chase switches on to me. Game.
That's not actually. Listen, big brand is focused on missing every time. If you can't pick up that brand, I don't know.
Yeah, that's true. That's something other than
It's not me.
It's not. Yeah, it's not you. You got a head. No, why are you hedging?
He was forced to switch.
I'm the way I buried it in his face.
Well, I'm not one of those cars.
So
You did to me. That's just irrelevant.
Yeah.
can I see yours? Because I think
At first, when we started the game, we weren't guarding Chase at all.
Oh, that's
And
it.
he won the corner, so we guarded him, and we didn't guard Sorgi, and it worked a lot better.
Do you guys have a videographer at the game?
For pictures, not.
Yeah,
Should maybe T Russo or go.
Yeah.
I don't know.
A lead coach.
It's like only a high man
That's
for
the
that
Oh,
person.
like experience. Wait,
That
what's
would
it?
be right. I don't know how to spell that.
Oh,
I don't know how to spell that either.
Not really good at their
We'll set up.
Oh, pues I'm not sure that stuff. Oh, it's quite free.
You did 20 of this.
I like
Oh,
that.
so I think we don't mess it up, and it would be called up in the progress. Otherwise. You're very welcome. Oh, Newton's over there.
No. Next Monday.
Yeah.
Like, so when are we doing this?
And still starting, we're having other quiz on Friday.
Well, that's Thursday.
Oh,
Okay, cool. Yeah, thank you for saying that. I need to get on to people about that. That's Thursday.
Yeah, the next.
So,
So, what if you,
this is Thursday.
alright, so if you find.
You still have that. We're on public, or do you all want to be?
Well, oh, yeah, I guess.
Yeah, we're doing
Yeah,
that.
we're
Okay, so he's still pushing it, but it's gonna experience regional subscription. Typically that friction is gonna pull
Oh,
it out the other direction. Yeah, so you got 10 more.
Okay.
So my question, I
Okay.
left, if you're, why would the track C?
No, I messed up.
When you're dividing out newtons by kilogram, and that comes from when we were talking about it in the lab last week. You have acceleration equals something over mass. And so we knew that this unit was meters per second squared because it's acceleration, and this unit is kilograms. So to get these things the same on both sides, this must have kilogram meters second squared. And then when we looked at, like, if you remember your graph,
I hit the game winner in your face.
you had an equation like y equals k over x. You guys, the number was like 2.5 or something, or 2, which was really close to the number of newtons that you had. And for all the groups, when we looked at that spreadsheet, for all the groups, this number that goes up here was really close to all the newtons. So what we said was, this number in kilogram meters per second squared is equal to the number of newtons. And so in terms of units, those things are the same.
So I could like run down the court
All right.
like over and over again, and I get tired, and like I couldn't do anything like that. So
Shoot.
Huh? Where were you? I have paper in the morning. So I talked to Chuck. Hey, Dan, there's a bad thing. We had like, we had to put bands around the bed and like hold them like this while they like did penetration shots down the
Oh, really?
shoulder, like hold them. And like,
I'm looking for.
Chief, you got mine.
Oh.
So area Q square.
Okay, so.
20.
no.
Can I see number one again?
So 1/2.
Huh?
So you use this, right?
Yeah, give me a second.
That's the area, that's the area. And that's squared, and then it's 40. 40 x squared. So then you
Area is.
You got it. Over on
I
the
know,
corner.
I can't find them in there because I don't know what they are. They didn't put them on like.
Wait, why are we doing?
Is that it?
Yeah, you're doing 20 right, the X squared.
and then, so this is
And
one.
then you have to divide it by,
Like, yeah,
divide it by half, so.
I would find this.
Did find this set.
Oh, so that's this is awesome. So
All right, hey, physics friends, I just sent an email to a few of you because you're on the list for not having signed up yet for Thursday's MLK activities. Within that email, so you should have an email from Shed, or however that's said, Sked. If you want to just search in your email for Sked, and it'll have directions for signing up. But if you're having trouble getting into that, so you should be using your email or username from the school district and then password.
Don't touch the board when I have the marker.
If you're having issues with that, you click on this link there, and you can just go to forgot password. And then within Shed, within Shed, everybody's got this password, West MLK 2019, okay? To get into the actual scheduling. You're going to want to do that today, though, okay? So if you get a little bit of downtime in class, I'm not going to be salty with you if you're signing up for this because this is what you're doing on Thursday of this week, okay? The 17th. No, I've got that wrong. It's next week. It's the 24th. Okay. So I was giving you bad info there. So it's Thursday, January 24th, but we need you to get signed up like today. Okay, hey? Donkeys that I just emailed that aren't clued in. We need you signed up today so that we can book these sessions and see which ones we need to have and which ones we don't need to have. Otherwise, you're going to get jammed into something that you're not necessarily going to be interested in. So right now, you've got an opportunity to decide which things you want to go check out. The one required session for everybody is this Voices of West High panel. So that's offered periods 1 through 6, okay, on the schedule. So make sure you've got that in there at one point. But then these other ones are offered a couple of periods. If you're interested in that, make sure you're signing up for that. And they're in here in order. So these are the things. Some things are individual periods. You saw somewhere like periods 1, 2, or period 2. This is periods 1 through 3. So race and restorative justice, that's a 3-period session. Okay? So there's a film on history of oppression, race relations, the necessity of restorative circles. You're going to engage in discussion, circle regarding impressions of the film. So that's a 3-period session. So be mindful of that when you're looking at these things too. There are a variety of topics. Blood donation, I think that's probably with Ms. Walling. But you have access to this list as well. You need to schedule today. Okay, this is for Thursday, January 24th. And I just sent you an email with sign-up info if you were not on the list for having been signed up already. Okay? So there's my moment on that. Be responsible. Take care of that yourself so you don't get placed in sessions you don't want to attend. If you didn't attend last year, it was a great day. There were all kinds of different things that you can try to tailor to your personal interests and a good opportunity to hear from some people from some different backgrounds and gain a little bit of perspective on different experiences that people have in the same community that you live in. Okay? Rough pivoting off of that back onto this thing. So again, it's a similar problem, but if we were doing a system schema for it, I've got person, I've got block, I've got floor, I'm probably going to have earth. The person's pushing on the block, so there's smoosh push there. The block is touching the floor, so there's smoosh push there. But there's mention here of friction, okay? And so, hey, it might not always say friction. The word you want to kind of clue in on is rough. Okay, it's a rough surface. And so that tells you kind of implicit, whoa, buddy. Rough is kind of cluing you in that there's friction. So I've got another line over here. And that's telling me on my free body diagram for the block, I should have 1, 2, 3, 4 interactions, 4 arrows there. All right, so make sure everybody at your table's kind of cool with the changes here, and then I think we'll just kind of power school, pick on this, come around, and add things to the diagram up here. Stop. Yes, you can.
So we found our slope, right? But do we need the slope anywhere in the equation?
Anywhere in the equation.
This equation?
Well, you're gonna need, so like this is the base,
Yeah.
and that's the height. Or you might say that this is the run.
But there's a
So
But wouldn't you
So
do
rise
work is this
over
the thing
run
weighs 100
has to equal
60
7.
pounds. Yeah,
No, because that's equaled out by that.
This is 0.7?
Yeah.
0.7. Okay. So you could write that equation somewhere. Acceleration equals,
She's asking.
well, let's talk about it. Just call this whatever. Sure. When you speak a letter. Which might be problematic in a second when we have run. Okay, and then in the equation,
Yeah.
the base becomes J. This becomes R. And what is the area of this thing? Okay. Okay, now over here, we can get rid of this. We can get rid of this, buddy. And make this be 0.7. So 0.7 equals R over J.
So 7 over 10.
Right, okay. Or if I multiply both sides by J, that's going to put J over here, right? Cancel that on that side. Okay. So 0.7J equals R. So down here, I can put 0.7J in place of R. Now it's just math, right? What do you think? J times 0.7J. Right on, buddy. And if you solve it out for
20
J, that's going to go there too.
y times x, right? No, 1/2.
Did I have 0.7?
Yep, Michael second.
Okay, so this is
That's what we got
you
here.
have to have L 40. No, and you have to put 7 to the x. But you have to have it in the equation so you can solve it. That's what she was doing.
No, then you just take this and you set it.
Watch what she's doing.
All right, so let's Power School pick on somebody to come chat with us. Boop. Spencer, come on up and add to our thing here. Yeah, I think so. There you go, sir.
And then we have to do
People might be mistaken in this, make sure you're paying attention in case you ask a question.
7.5.
Or maybe you generally have a question on something. Genuinely.
So do 0.7 times 7.5.
What is that again? Ooh, wow, this is.
Just go ahead and put like the stuff you know right now, and then we can come back and do this later, Spence. So what do you think the graph shape is going to look like?
Touch buttons.
questions or concerns for Spence based on that? So if you scroll back, you can kind of just use your finger and scroll there. If you look at like what we were saying on the previous one, go look at the previous problem.
Oh.
So keep in mind, this thing's starting from rest, what that tells you about your graph shape. It's going to start from a velocity of 0.
So it should go that way. Do I hit this to
Ooh,
erase?
yeah, so the closest button to the tip is the eraser.
Closest button to the tip is eraser. Okay.
There you
Yeah.
go. Got it. All right, so we're looking for that for the graph shape. Now you got this other piece of information you have about the motion, the 20 meters. Where's that going to go? And you can scroll back up to the other graph if you want to double check yourself.
Here in this area.
So that part is not going to change here. Still going the same distance. All right. And that's all we know right now. So you can go ahead and get rid of the numbers on there. We'll pretend we don't know those at the moment.
Even the 20?
The 20 we do know, but
Okay.
The base and the height we don't know yet. All right, cool.
You want me to do it?
Do you want to go back over to Power School and pick on somebody? Hit the select button. Key. Pop on up and draw something for us. Yeah.
How do I do this? This little key.
Okay. So eventually we're going to end up with an acceleration versus time graph. Initially, you're not going to know what the acceleration value is key. Go back over there to Power School, pick on somebody else as well. But all we are knowing is that in this model, that acceleration versus time graph is going to be horizontal. And hit the select button.
It's random.
BG's not here. Gus again. Hey! And you can like scroll with your finger if you need more space. So we got the 4 arrows that agrees with the 4 lines connecting to the block in the system schema. We got 3 newtons of friction, 100 newtons of smoosh push, 100 newtons of gravity, and 10 newtons of smoosh push from the pusher. Questions or concerns about any of that? All right, sir, go ahead and bounce back over to Power School, click on somebody else. Whoa. Don't do that. All right. Yeah. Pop it up there, one note for us.
The notebook.
Which one is it?
Bottom.
Here?
No.
No. No. Is this it?
He's got like arrows thing that kind of looks like it wants to expand it.
Oh, alright.
Ah, there you go. Yep. All right, can you talk to us what you got there, sir?
I have the different forces, okay, and then I have the FU down below, and then the friction.
Okay. So we've got 10 newtons to the right. We've only got 3 newtons to the left. That means in total we're unbalanced by 7 to the right. If we had 10 newtons of friction, this thing would be balanced, but we don't. We only have 3, so we still have 7 newtons unbalanced pointing to the right. All right, thank you, sir. And then I'll hop on it from there. So this is kind of how you use the tools to get back and forth between the UBFPM and the CAPM. So we have the unbalanced force now. That's kind of the critical thing from the diagram. I'm going to take that 7 newtons. Ah, boy. Oh, that's sad. Ooh, we might need a new pen. Battery. We've got the 7 Newton FU. You've got 10 kilograms of mass. And so you're going to have an acceleration of 0.7. So I'm using the force addition diagrams to tell me there we go. 7 Newton FU, 10 kilogram mass. And that's going to tell me I've got 0.7 meters per second squared of acceleration. There was a question earlier on where this whole thing comes from, that if I take newtons over kilograms, I get meters per second squared. And that was the lab that we started this off with. You had an equation for your graph that said acceleration equals question mark over mass. And you got some kind of number from Desmos ranging from like 1 to 3. And you had to put a unit on it so that the equation made sense. If you have acceleration on the left, you have mass on the bottom on the right. That number for your graph, the constant, had to have the units kilogram meters per second squared. And we found in the end that the number of kilogram meters per second squared was very closely related to the number of newtons of force you had. So that's where we established these things are equivalent. So anywhere that you have newtons, you effectively have kilogram meters per second squared. Then when I divide that by kilograms, I get left with just meters per second squared. All right. So that's telling me that the slope on this graph is no longer 1. Now it's 0.7 meters per second squared. So if this was 1, this would be 0.7. Okay. If this was 2, this would be 1.4. If this was, let's just call it T, this is going to be 0.7t. That's how slope works, okay? So now if I go to calculate that slope, and I put 0.7t over t, I get that the slope is 0.7, okay? So jot this down somewhere for yourself, please, because it's something you're going to have to do fairly regularly on these types of problems. That if I know the slope, but I don't know the base or the height, I'm probably going to have to solve them in terms of each other. So now if I go to write my area equals 1/2 base times height thing for the triangle, the area of that triangle is 20 meters. The base of it is t. The height of it is 0.7 t. This is going to become 20 equals 1/2 of 0.7 t squared. Or you could maybe just kind of note, like, hey, what have I written here? I've written the change in position equals 1/2 the acceleration times the time squared. Okay. Solve this out. Multiply both sides by 2. That's going to be 40 equals 0.7 t squared. So 40 over 0.7 is t squared, and that's going to give me a t of something in the 7 ballpark, 7.55, okay? 7.55 seconds. So now we can come back over here. This is 7.55 seconds, and I can figure out what 0.7 times 7.55 is. That gives me that velocity. What'd you get for that, Hayden? The velocity. 5.29, okay. 5.3 meters per second, okay? So again, that's just kind of solving things out using the tools. Now, problem 3, once this block has traveled to 20 meters, so we got our velocity versus time graph. This thing has traveled the 20 meters. It's going to have that velocity of 5.3 meters per second. The person stops pushing it. So if you look at the free body diagram, this force is going to go away. Now the free body diagram is going to just have the smoosh push up, the gravity down, and the friction. And think about what that does to your force addition diagram. And so basically what you're going to have to do, so this is problem 2. Problem 3 is what happens to the graph after that. So what's happening on this velocity versus time graph after the person stops pushing? So go ahead, we're not going to get it completely done today, but maybe in a different color on that velocity versus time graph. Think about how things are going to change. What's going to happen if you take away the smoosh push from the person? Okay. So go ahead and modify your free body diagram, modify your force addition diagram again. What's going to happen to this object? We're no longer pushing it, it's just got friction acting on it.
Keep going.